Hey guys, welcome back. Today's lesson, I'm not so sure I'm going to be able to do a good job of this on a video. So it's really a very visual lesson, and I'm not quite the artist that I need to be to do this on a video. So please, I hope you watched the Khan Academy videos just to get a better idea of what these shapes actually look like, okay? Okay, so I also made a worksheet with these notes, these same exact problems on one sheet of paper, so you didn't have to write it all down. But here's what a sample problem would look like. You're basically going to start with a flat surface of some sort, and then coming out of that flat surface is different shapes, like squares. Kind of like a loaf of bread sitting on a table. The table is the flat surface, okay? And then you have a bunch of slices of bread that are square-like. Okay, something like that. Well, to help you visualize it, I have a program I'm going to show you here in a second. Hold on. Okay, so for this problem, we're going to start with a circular base. So the base that's flat is a flat circle of a radius of 2. Okay. Coming out of that circle is going to be squares. See in yellow where it says squares, okay? So coming out of your computer is a whole bunch of different sized squares, okay? There's actually a square sitting here, coming out of the screen though, and another square here, and another square here, and they're coming out of the screen, making a solid figure. Now that's really hard to visualize, so I'm going to use this program to help me do it. So here, it says show chords. That doesn't really help many people see anything. That's no biggie right there. Okay, we're going to have to get 3 dimensions. So we have the x and the y axis drawn flat right now. We need to add what's called the z axis so that you can see the 3rd dimension. So what you're seeing right now is still that circular base, but now I've added an axis going straight up. Okay, now here's 4 squares. That still doesn't really help you see what it looks like. I can try rotating it, but I really still can't see it. Okay, I can try sweeping the different size squares, see if you can get a feel for the shape. Usually that doesn't really help people either. So here, now I'm going to create the solid. Watch how cool this is. Bunch of squares, bunch of square slices. You see it? So that's the solid itself. Here are those square slices. Here's 4 of them anyway. Okay. Let me rotate it so you can visualize it. Notice it has some rounded parts even though it started off looking like a square. It was one square. Now there's a whole bunch of squares actually going across there. Okay. Each of these is a different square. So to be honest with you, whether you can visualize this or not is really not hugely important, but I do need you to understand that you're basically going to be finding the volume of one slice, okay, and then adding up all the slices by integrating. Now when I say volume of one slice, we're actually going to find the area of the square, multiply by its width, but we're going to call the width dx, change in x. And that will turn it into the volume of an infinitely thin square. And then we're going to add all of the squares going across with integration. All right, so I don't know if that helps visualize it or not. That's the best I can do. But honestly, even if you can't visualize what the shapes look like, I can still show you how to do the math. Okay, so here's a typical problem. This is about as easy as I could make it. All right, the base of the flat solid is the shaded region between x squared and 2x. So we're going to start just like we did with all of our other volumes. So first graph it and find where they intersect. To find where they intersect, I'm going to set them equal. Then set it equal to 0. Factor. And we get that they intersect at 0 and 2. Okay, so remember that 0 and 2 were my points of intersection. Now when I graph it, I know I have a parabola and a line with a y-intercept of 0. That's it's a positive line. But I also now know that it intersects at 0, and this would be 2. Okay? So this is the shaded region we're dealing with right now. I'm going to draw that a little neater. Hold on. I told you I'm not much of an artist. Okay. So now, if I needed to know the coordinates of this point right here, well, x is 2 right there. And if I plugged in a 2 to either of these two equations, okay, then you'd get that y is 4. So that tells me that the coordinates there are 2, 4. If I needed to know how far up it goes up 4. All right, now, cross sections are perpendicular to the x-axis, and they are squares. So we have, sitting in this shaded region, we have squares that are perpendicular to the x-axis. So they're sitting like this way. And those squares are coming out of the screen. Different sizes. This square is smaller than the square in the middle. But we're going to write the equation or the formula for it in terms of x, and it'll take into account different size x's depending on where it is in that region. Okay, so here's your main idea. We're going to find always the area of one cross section. So we're going to find the area, in this case, the area of a square. We're going to find the area of it. Multiply, give it some width. We're going to multiply by dx, which is change in x, an infinitely thin strip. Okay, so that now gave it some width, so that this now represents not just the flat square, but now it has a tiny little bit of width on it. So now it's the volume of one square. So this is now volume of one square. Next, and you're going to do that every time, it's the area of one slice, whatever shape that slice is. Then we're going to integrate all the squares going across this one, this one, this one, this one, this one. So we're going to integrate from 0 to 2, and that will add up all of the volumes, all of those squares, and that's how you get the volume of that solid figure. Okay? So basically you're taking the area and integrating it is turning it into volume. Okay? So now I'm going to clean this up again in a minute. The next thing we need to do is figure out, how do I represent the area of that square? Okay, well, the formula for the area of a square would just be side squared, or x squared. Whatever the side is, it's length times width, but they're the same. Okay? Now we got to go back to that picture. So the length that's right here on this square, where is it on my solid figure? It's actually sitting from here to here. Okay, well, how do I find a length between two curves like that? Same as we did before. It's going to be top minus bottom to get that length. So this formula is going to be the length of one side of my square squared, because it's length times width for a square, for the area of a square. Well, what is the length of that side right there? It's whatever this top curve is minus the bottom curve. Well, the top curve is the line, so it's 2x minus x squared. And that is how you find the volume of that solid figure. Volumes by slicing, or volumes by cross sections. Okay, the general rule is going to be find the area of one cross section using basic geometry. Okay, and then integrate to add up all of them. I don't really care about the final answer on this because I know you know how to work that out. You could FOIL it and do it by hand, or you could use Math 9 in your calculator. I'm just going to focus on the setup, okay? All right, so go back to what we did. First, we graphed it, found where they intersect, draw in the slices, and find the area of one slice. The dx gives it some width, which technically makes it like paper thin. Now we have the volume of a super thin slice, one slice, and then the integral adds up all the slices going across. All right, so now all we're going to do in the next problem is change it so that it's not a square. Okay, so all of this work over here where we set them equal and all of that, that's going to remain the same. So you may want to, in your notes, quickly draw that graph again. Okay, so cross sections are still perpendicular to the x-axis. Okay, so we're still going to be adding going across from 0 to 2. Okay, but the shape is now a right triangle. So we're going to have to find the area of a triangle. And that's basically the only difference. Okay, now it's an isosceles right triangle. Okay, the formula, or that means these two are the same. The formula for the area of a triangle is 1/2 base times height, but since it's isosceles, it's going to be 1/2 of whatever this length is squared, because they're both the same. Okay, so 1/2 of whatever the length of that is squared. We call it s squared or whatever you want to call it. Okay, so my formula is going to be 1/2 base times height, but they're the same. So I'll just square it. And now we got to figure out what that base is. Well, it says that it's the leg is sitting in the base. This is the leg, and that's what's sitting from here to here. Okay, so from here to here, what is that length? It's just top curve minus bottom curve, 2x minus x squared. So it's almost the exact same thing as the last problem, except for this 1/2, and that's simply because the formula for the area of a triangle is 1/2 base times height. So once again, same thing. Find the area of one slice and integrate it to add up all your slices going across. Okay, the next one's going to have the same picture again. All right, this time it's a rectangle sitting in the base. Okay, but the base is the same shaded region. So draw another one. Okay, cross sections are perpendicular to x again. So we're going to be adding our slices going across from 0 to 2 again. That's not changed. However, the shape that's sitting coming out of that base is a rectangle, and the area of a rectangle is length times width. So area of rectangle this time. Okay, but the area of a rectangle is length times width. Length times width. Okay? So we're going to have to find the area of the rectangle. Well, it says the length is always twice the width. And the length is what's sitting in the base. So sitting in the base from here to here is the length. Well, we've already found that length, top curve minus bottom curve. That length is the line minus the parabola. Well, that would be the length of the rectangle that's sitting here. Okay? The width, the length is always twice the width. Well, if this is supposed to be twice that, then I guess this is half of that. So this would be the same number, but half of it. Okay? So let's see if that makes sense. It's the length sitting from here to here. So we subtracted top curve minus bottom curve. The length is supposed to be twice the width. So I kind of had to reverse that, make sure this one is double this one. All right, so now let's put it all together for my formula. The area of my rectangle is going to be this times this. Well, since the numerators are the same thing, I'm going to take this 1/2 and just move it out front instead. So it's going to be 1/2 of 2x minus x squared, but there's two of them, so squared. And that would be my formula, dx. Okay? All right. Now, what do you think would change in this problem if I said the cross sections were perpendicular to the y-axis instead of x-axis? Okay, let's say I changed that to be y-axis. Well, if you change this to a y-axis, now your slices are going this way. And so in order to add them up, you're going to have to integrate y using y bounds from 0 up to wherever it stops, which is 4. Well, as soon as these are y bounds, if I have to change these to y's, 0 and 4, if these are y's, then I'll have to express all of this in terms of y's also. I'm going to do that in the next problem. Okay, go ahead and graph the shaded region one more time. Okay, this time cross sections are perpendicular to the y-axis. So you want to draw them going this way, perpendicular to the y-axis. And that means we need to immediately find our y bounds from low to high. Okay, well, the points of intersection, those were x values of 0 and 2. So we would plug in the 2 here and get that y is 4. So now I know immediately that I have y bounds that are going to go from bottom up 0 to 4. But because those are y bounds and people forget to change everything to be in terms of y, you may want to write y equals 0, y equals 4, even though you don't technically have to. Hopefully that'll remind you that everything now needs to be written in terms of y, not x. Okay? So knowing that, I'm going to rewrite these two equations in terms of y. For the parabola, take the square root of both sides, and you'll get that x is equal to the square root of y. It's actually plus or minus the square root of y, but we have only the positive side over here. The other side would be negative square root of y. All right, now solve the line. Solve for x, divide by 2 on both sides, and we get that x is equal to y over 2. Okay, so now let's look at what is the shape of our cross-section. It's a semicircle. Semicircle. So we're going to be finding the area of a semicircle, or half of a circle. Okay, and technically I should have a dy. All right, well, the formula for the area of a semicircle, if it was a whole circle, the area would be pi r squared. But since we only have half of a circle, it's 1/2 pi r squared. Okay, so I'm going to come over here. I know I have y equals 0 and y equals 4. And I'm going to have a 1/2 pi r squared, where right here I have to put the radius. Okay? But what is the radius? This is the diameter, and it's the diameter that's sitting in the base. So sitting from here to here is actually a diameter, but what I need is radius. So what I would suggest right away, write these parentheses, and pretty much for all of these, I'd go divide by 2, because the diameter is going to be what's given. The diameter will be sitting from here to here, but radius is what's needed for the formula. Okay? Now mathematically, you're going to be squaring this 2 and squaring whatever that length is, diameter. Okay? So now I can fill that in. What is that diameter? Well, I have to figure out what the distance is from here to here. Remember, go from right to left. And so it's parabola minus line. So the parabola is the square root of y minus the line, which is y over 2. Okay, now let me show you. That's it. That is the setup. But even putting this in your calculator would be messy, okay, let alone solving it by hand. So let me show you now how to clean this up. But before I do, you may want to hit pause and rewind. Okay, remember, it's 1/2 pi, and this is r squared, but it's always the diameter that's given, and that's why you have that divide by 2. Okay, now how do I clean this up? I'm going to take the 1/2 pi and move it out front. I'm going to be, so that's now taken care of. Okay, I'm going to apply this square to the entire numerator. Okay, and I'm going to apply the square to the denominator, which will make it a 4. 2 squared is 4, but it's on the bottom. And I'm actually going to move that out here also. That way, only this has to go into my calculator, and I can just bring this down. So what do you really have out front? That's really a 1/8 pi. Okay, and now it's a little bit easier to put this in your calculator or to work it by hand. Either way, okay? So again, I moved the 1/2 pi out front, and on the back side over here, I kept this squared, but this 2, I squared it, making it a 4, and moved it out front. Okay, it's actually in the denominator. And from here, you can put it in your calculator or work it out by hand. All right, guys, hopefully you were able to hang in there for that. The worksheet pretty much is just like this, and I tried to show my work on the solutions that I posted. I posted just the answers in one page, but I also did worked out solutions on another page. This is usually a pretty tough lesson for day 1, so hopefully you're hanging in there. We'll work on it again tomorrow. All right, bye. Good luck.